In the previous section, we have defined what vector spaces and bases are. In particular, we find that the bases are our coordinate system, the coordinate system of a given vector space. So the way we view the vector space. But we notice that we can define several coordinate systems on a vector space. So we find several bases of a given vector space. Now we want to leverage this concept and, given a vector space, be able to change the basis, so change the point of view. To do so, we will define the linear mappings. We define a linear map as a function phi that goes from one vector space V to another vector space W, and follows two conditions, the additivity condition and the homogeneity condition. As you can see, the additivity condition says that applying the function to the sum of two vectors is the same of applying a function to the x vector and the y vector and sum the two results together. Homogeneity is basically the same with the scalar multiplication. Let's take a look to an example of what is a linear map. And for example, we will take a look to this f function in a 2D plane. So this function takes two arguments, x and y, and give us a new vector on the plane that has the double of the x coordinate. As you can see, a goes from is here, f of a doubles the x coordinate. Let's see if how the additivity condition works. We see that the two vectors are here, the green and the blue one, and it's the same of applying the function to to a plus b, or to sum the result of f of a plus the sum plus f of b. The result is the same. As you can see, the blue line, the green plus the blue line points to the same point as the red one. The homogeneity condition is the same. As you can see, the two vectors after these two steps point in to the same coordinates. But please notice that not all functions are linear mappings. For example, let's take a look to this f. We can try if the condition of additivity is verified. So let's select two random vectors. Here I took 1, 1 and 2, 2. So if the additivity condition, this f of the sum of two vectors should be equal to the f of the first vector plus f of the second one. But that's not the case, because here we have the sum that gives a vector of coordinates 3, 3. We apply the function that takes the square of both elements, so we get 3 to the power of 2 is 9, so 9, 9. Here, instead, we apply f to the vector of 1, 1, 1. And we get, of course, 1 to the power of 2 is always 1. F of 2, 2, instead, gives 4, 4. The result here is a vector that has coordinates 5 and 5. These two results are different. So this function violates the additivity conditions in a condition, so it's not a linear map. There are several there are three types of linear mappings, special types of linear mappings. In particular, if a generic linear map that goes from V to W follows this condition that we will see in a minute, the function is said to be injective. So phi is an injective linear map. We say this when we take into two random numbers, random vectors on V, and we see that the images on W of these two vectors are the same, then the two vectors must be equal all to the other. So if this condition is verified, we talk about injective linear maps. Here we see an example. So let's take a look to what it means to be injective. So we take 2 points here, 2 points, and we go on B. For example, we take 2 points here, and we go on the same image, because here is the statement. So x, y go to the same value. But if the linear map is injective, then these 2 points must be the same. That's the case here we have of an injective function. So injective linear maps can be said to be one-to-one mappings. Other than injective linear maps, we can define the surjective linear maps. And we say so when the function takes whatever element on V and gives always an element on W. So applying, we can say that the image of the V vector is equal to the W vector space. Let's take a look to an example. For example, here we have that all elements of this will be W are take an arrow. Here we have, as you can see, these 4 elements of these 3 elements always have at least one arrow pointing to them. Here, where the linear map is non-surjective, we see some elements that have no connection between the left vector space. We can also say that a linear map is injective but not surjective, or the linear map is non-injective but surjective. Depends of the cases. When both conditions, both properties arise, we say that briefly that the linear map is bijective. So we have injection, surjection, and when both of these conditions are proved, the function, the linear map, is bijective. So linear maps in linear algebra are said to be a special case of homeomorphism. Homeomorphism are maps that preserve some sort of properties conditions between two algebraic structures of the same type, of course. For example, in linear maps, the two algebraic structures of the same type are vector spaces. We have defined V and W, that phi goes from V to W, two vector spaces. Okay, and which structure does the linear map preserve? Well, the linearity, so the addition and homogeneity properties and conditions. There are special cases of homomorphism in the context of linear maps, and these are isomorphism, endomorphism, and automorphism. In particular, we notice and remember that endomorphism are functions that goes to a given vector space to itself, and of course are linear. Automorphism have that property, are a special case of endomorphism in which the function phi is also bijective. Now let's leverage the concept of basis on a given a vector space and linear maps and demonstrate proof how linear mappings can be represented using matrices. So consider again two generic vector spaces V and W, and we define on top of them some linear mapping, a generic linear mapping phi. We can say from the previous section that we find that in V there's a basis B that has n vectors, and W that has a set that we will call C that has m vectors. Since phi is a linear map and follows the two conditions we have mentioned before, we can take always phi of a vector in V and say that this is an image on V, on W. So phi of B of J, which is a generic vector, a special one because we took it from the basis of the vector space V, but don't worry. If we take the image of this vector, well, this will be a generic vector in W. A generic vector can be written as a linear combination of the bases, as we've seen here. The basis of W is C1, Cm. So we say that a generic vector of W is the linear combination of the bases. This alpha 1j, alpha mj will be our coefficients. Of course, we can represent every element of the basis in V as a linear combination of the basis in W. Of course, the function applied, the linear map applied to each vector B. That's pretty fine. Now we can take a look to these coefficients, because this, remember, as a system of linear equations. So we can write all these coefficients in a matrix, which will be called the transformation matrix of phi, because it depends on the linear mapping between the vector space V and the W. Please notice that here each phi of B, of our generic phi of B, is a column. So we have alpha 11, alpha m1. Here we have alpha 11, so alpha m1. So basically we have transposed these coefficients. Here we see on a horizontal line on the matrix, we put them vertically. Why we do this representation in this way? Well, because if we take the coefficients, if we take a generic vector of x and we represent it with the basis B, then these lambdas will be their coefficient, its coefficient. Then we take the image of phi of x, which is y. It could be, this vector could be represented with the basis c and some coefficients. These two are said to be coordinate vectors. Then, from this, remember, here we have the basis, but we can put it a generic vector of v. So, given these coordinate vectors, we can write that the coordinate vectors times the transformation matrix gives us the coefficient vector in W. So we find a way to go from V to W using a matrix. So that's why we have just represented a linear map with a matrix. Here we have. This could be seen as phi of vector x equals y, vector y. So the transformation matrix can map coordinates with respect to a basis. Remember that this A and these coefficients are defined from a basis in V. This comes from a basis in B, and the coordinates with respect to a basis in W. Here we have the coefficients of a generic vector y with respect to the basis in W, the C basis that we have selected. So with this property, instead of define and find some complex functions, we can simply define our transformation matrix that is much simpler. So, for example, let's take a look to this original data that is a square with some dispersion. Okay. Now, if we apply a linear map that has this A1 transformation matrix, then we are applying a rotation by 45 degrees to these points, to these vectors. So as you can see, the square rotates by 45 degrees. With another linear transformation applied to this original data that has this transformation matrix, we can stretch the data along the horizontal axis. Why? Because, as you can see, here we have 2 instead of 1 on the x coordinate. So these vectors that are also points on a plane will be doubled by their x coordinates. In here we do some linear general linear mapping. Please note that as I mentioned before, here we are working with a linear transformation, a linear map that goes from the plane R2, r to the power of 2, to r to the power of 2. We are modifying the way we view the points and the points themselves. Now, we've seen that linear maps can be also bijective, and this property, or better, the injective and the surjective properties are very important, because here we don't prove this concept, but it can be very intuitive. if the linear map is bijective, then the transformation matrix is invertible. We can find the inverse of the transformation matrix. So given this expression that allow us to go from V to W, we can come back and go from W to V, of course using the same basis, by taking the inverse of this transformation matrix. For example, if we take this a plane and we define this basis A1 and A2, the canonical basis, then using some linear map that has this transformation matrix A of V, we go to this generic basis B1 and B2. Fine. The vector we already seen is the same, but the coordinate system is changed, so also the coordinates of x are different from one plot to the other. If we want to come back and from this perspective come back to the canonical basis, well, we can apply the inverse of the transformation matrix to these vectors, or better, to the coordinates of these vectors. We are doing an automorphism because the linear map behind this transformation matrix is injective, surjective, and of course is a linear map. Now I want to discuss with you about basis change. Don't worry, the concepts will be a little bit complex, but we will come back in further courses, in particular when talking about matrix decomposition. Here we will take a look to a general presentation of the concept of a basis change. We will generalize what we have previously said. So we consider again two generic vector spaces, V and W, and a linear mapping that maps V to W. Okay. Before we have defined two bases, one for V and one for W, that we called B and C. Now, somehow, we can say that we have found another basis, B tilde and C tilde, respectively on V and W. Okay, it's legit. As we defined before, we can always, since we have this linear map, using the basis B and C, we can find a transformation matrix A of phi. Using some different bases, we can find the theory is the same, another transformation matrix that we will call A tilde. But how now? Since the two function and the linear mapping is the same, the linear map cannot change if we change the basis. The concept behind it should be the same. So there must be a way to go from A of phi to A tilde of phi, for example. But how? Well, we can do so using a change of basis. But let's start with this, taking a look to the V vector space. Since B is a basis, we can write every one of these vectors as a linear combination of the basis. Okay, that's fine. This S1j, S and J, are vectors if we define this linear combination for every n vector, for each of the n vectors of the basis b tilde, we get a matrix that is a transformation matrix from b tilde to b. It's also an endomorphism, again, because we go from v to v, from this basis to this basis. The transformation matrix from b tilde to b will be, we denote this transformation matrix as S. Of course, this matrix is squared, n rows and n columns. We can do the same with the W. We have the two bases, we express the tilde one with the others, the basis C. We get this coefficient. Since we can express every vector of C tilde, we get a matrix, a transformation matrix that will be denoted as T, that has m rows and m columns. We go from C tilde to C once again. So here is the idea on how we can go from how we can do a change of basis. So here we have A of phi, that from this on the left we have V, the vector space V, and on the right we have the vector spaces W, the vector space W. Here is what we know. Phi expressed as with the B and C basis, A of phi. We then get this A tilde of phi. Now we want to find a way to write this A tilde or as a function of A of phi. To do so, we need to involve this matrix, of course. So A tilde goes from B tilde to C tilde. Okay, but we can go around this function. So we can take the vector space respect to B tilde. We can change the basis, go to B, then apply our transformation matrix, which brings us to C, and then from C, some way, go back to C tilde. So let's start with one way. Since the two, we will follow, the arrows. So our goal is to go to C tilde, but since here we can go all the way around because T points from C tilde to C, the idea is find some relationship between take this path to go from B tilde to C and this path. Let's start with the bottom one. So B tilde, we apply phi on a generic vector of the basis B tilde. Okay, it can be expressed using the transformation matrix A tilde with the basis C tilde. So here it is. These are the A tildes are the coefficients inside the elements of this matrix. But again, we are now in W, and we can express these C tilde vectors using the basis C. So again, C tildes are on a linear combination of the C vector basis. We then As you can see, these are these T elements are the elements of the matrix T. Okay, so this, so the function phi applied to a generic vector of base b tilde is some linear combination of the vectors of the C basis and the sign coefficients that can be expressed using the elements of the T matrix and the A tilde matrix. Okay, so we have done this. We have followed these two arrows. Now let's take a look to the two above. So same thing, we want to apply psi to b tilde. So we want to go from V to W. But now we will take this path above. So b tilde can be written using the basis B. The coefficients of this linear combination are the elements of the matrix S. Okay. Now, using the conditions of linear mapping, in particular the additivity condition, phi of a sum is the sum of the phis. So these coefficients go out, and we can say that phi of b of I is, we are now from here to here, the linear combination of C respect to the C basis. So we get these red terms in which this A L A are the elements of the our transformation matrix A of phi. Wrapping up, we can say that phi of b tilde vector, base vector, is a linear combination of basis C and these coefficients that came from the A transformation matrix and the S matrix. So we have find these two expressions. Here we have followed the below path. So from B tilde we mapped to C tilde and then go to C. Here we have tilde and A tilde, and here we have done S and then A of phi. Since the two expressions are the same, then these two terms must be equal. So the coefficients of the linear combination of CL vectors must be the same. So this one must be equal to this. Here we go. This is generic for every J and of course L. These are the coefficients of T, A tilde, A, and S. And please notice that here we are writing a multiplication between matrices. As you can see, the K index are the ones that are summed together. You can see here the I indexes. So this can be written in a more general form using matrices. T of A tilde equals to A times S. As you can see, again, we have to write each term from right to left to follow the path. So we say, for example, here we have done S and then A, okay, and we see as A. Here we have done A tilde and then T, and here we have A tilde and then T. Taking the inverse of T, we will not prove that T is invertible and so on. Taking the inverse of T, here we can express the A tilde matrix using the transformation matrix of defined with bases B and C. Here, taking the inverse matrix of T means that we reverse this arrow. So what we are doing is saying that A tilde, which is from B tilde to C tilde. Okay, nice. We have just the path has only one arrow. But the long way means that, remember, we have to read this equation from right to left. So from B tilde we go to B, from using S. From B to C we go to using A, and then from C to C tilde we use the inverse matrix of T. Here we have S A T minus 1, T to the power of minus 1, the inverse. Why we have talked about this basis change? Well, it's very useful, especially in some particular problems, to redefine the transformation matrix in a convenient form that is particularly simple to compute. So if we are using, for example, canonical basis and our matrix is a mess to compute, we can find some other basis that, for example, will simplify the transformation, and we've just to define this P and S matrices to go from a complex representation of a matrix to a simple one. Don't worry, this was the basis change is a little bit abstract right now. When talking about matrix decomposition in another course, we will see in detail how these concepts can be made more real and realistic. So what we have learned in this course number 1 when we talked about linear algebra. So which is the content we collect from the depth of abstraction and we want to bring with us in the next videos? Well, there are 3 key points. The first one is about vector spaces, and we have found that a vector space allows us to introduce some, let's say, obvious operations and properties between its elements. That these elements are called vectors. A vector space is a general environment that allows us to define whatever elements we want. That's a pretty powerful concept. Then with a particular case of vectors or elements inside a vector space are matrices that represent vectors in a R m times n space. And matrices are a compact way to represent vectors and to compute multiple simple operations in one shot. When we do, for example, an addition between matrices, in reality we are doing multiple simple operations element-wise. The third key element are the bases. And the bases define how we view a vector space, and we have already seen that linear mappings allow us to change this perspective and go from one basis to another, using the matrix representation of linear mappings. So thanks to linear bases are the skeleton of a vector space and the coordinate system. So how we perceive the vector space. With linear mappings, we can change this perspective. Again, using matrices is always much simpler. So in this course, we've built some very powerful tools. And in the further one, we will build something great using those tools. Thank you.